Okay, so we are going to do a full analysis of this function right here. So I have kind of listed out for you maybe some of the things that we might be interested in looking at. So in advanced functions, we talked about functions being even, odd, or neither. So that kind of tells us something about the function's symmetry, or if it has no symmetry at all. We're going to talk about the domain. We're going to find the intercepts, x and y. So this is all ABC. This is all from the original function. And then we're going to classify critical points, find them, identify intervals, and then we'll talk about intervals of concavity, so first and second derivative, points of inflection, and then we'll graph. This is literally everything, right? So I think that this is pretty comprehensive. If we're doing a full analysis, this is everything that we'd kind of be looking at. So can somebody remind us about even, odd, or neither? What does this mean? Devin?
Isn't it when it's like f of x equals a number if it's f of negative x and they equal each other? It's even. And then if negative f of x equals f of negative x, it's odd.
Yeah, okay, so that's the algebraic definition. That's good. So Devin says if we sub in, if f at x is equal to f at negative x, that is even, and she's correct. And then if f at negative x is equal to negative f at x, that means the function is odd. Now, what does even and odd mean, just at the base foundation here, just so we can remind ourselves? Mark?
Even like starts from one direction and ends in the same direction, and also has symmetry over the y-axis.
Okay, line symmetry over the y-axis. Good. And odd functions, Anil?
Has point symmetry at 0, 0.
Very good. Point symmetry at 0, 0. And then, of course, there is a neither option where it has like neither of those two things. So it might have some type of symmetry, but it's not our specific line symmetry on the y-axis or point symmetry at 0, 0. Okay, so one little quick check. I don't think it's super necessary that we do these like substitutions or anything like that. One little check that you can do just to see if something's even or odd is, does it have all odd exponents? Does it have all even exponents? Or does it have a mixture of both? So this one, we can see it has exponent 3, exponent 2, and exponent 1. So it has a mixture of even and odd exponents. So I know right away that this is neither even nor odd. Okay? So I'd be looking at those exponents. Even functions, they can have a constant. The shift does not affect where that line symmetry is. But odd functions, if they have a constant, it will shift up the point symmetry from 0, 0. So odd functions would not have a constant. But this guy's got a mixture of even and odd. So we would say that this guy is neither. Okay, of course we know it has an odd degree, so I actually do know that this has opposite end behavior. That also tells me about something about whether we have any absolute maxes or mins. If I have a function that has opposite end behavior, is it possible that this function has an absolute maximum or minimum? It goes in either direction forever, right? So odd functions don't ever have absolute maxes or mins. They might have local, but not absolute. Okay, domain. So with that, knowing that it has opposite end behavior, what's my domain? Yeah, it's just everything. So you can say x is an element of real numbers, or if you want to use interval notation, you can say negative infinity to positive infinity. Intercepts. Okay, I'll do that down here. Intercepts are going to require us to factor. So I'm just going to start by taking out a common factor here. Make our life a little easier. And then I think two things that multiply to 6 and add to 9 are 3 and 3. So we actually have x plus 3 squared. Okay, and usually we set f of x equal to 0 when we're solving for x-intercepts, because x-intercepts have y values of 0. Okay, so my x-intercepts are 0, 0, order 1, and negative 3, 0, order 2. Somebody remind me what these orders tell us about our function? Mark? Yeah. Great. So order 1, that just goes straight through our x-axis, whereas order 2 kind of bounces off our x-axis. Good. Olivia?
How did you know it was order 2?
I'm looking at the exponent on here. So because the exponent is 2 there, it's order 2. And then because this exponent is 1, that one's order 1. Okay, the other intercept that we want to find is the y-intercept. So I sub in 0 for x. And I think we can kind of already see, I almost said Cardi right there. I think we can almost already see here that because we have an x-intercept at 0, 0, that's also where our y-intercept is. So I think we can just say it's equal to 0. That's the y-intercept. But if we need to find a y-intercept and we don't have an x-intercept at 0, 0, we're just subbing in 0 for x and simplifying. Okay, so there's our intercepts. Okay, now the calculus part, right, part D. We're going to find the critical points. So when I think point, I want to think x, y coordinates. So I want to know what those are as x, y coordinates. We're going to use our chart. We're going to find extrema and classify them, local min, local max, intervals of concavity, that good stuff. Okay, so I'm actually going to show you how to do this all together rather than doing 2 separate charts. Okay, and it will give us maybe a bigger picture of what's going on with the function. So of course, firstly, I just want to find the first and second derivatives. So let's start with that. Not 6. Okay, I want to know where the first derivative is equal to 0. And I'm going to just common factor on the right-hand side as I'm doing that. So I am factoring here to find the x's. I think that gives us plus 3 and plus 1. Multiplies to 3, adds to 4. Okay, so I saw maybe like a few people in my assignment marking that assumed that the y-coordinates of these guys were 0. The y-coordinates on the first derivative, we need to actually just calculate those with the original function. So I'm just going to do that over to the right-hand side here really quickly. We'll evaluate f at -3 and f at -1 so that we have their y-coordinates. So just subbing these into the original function to get the critical points. Okay, I'll let people out there calculate those quickly for us. What'd you get? Did you get the same thing?
I got f at -3 is 0, and f at -1 is -4.
0, does that make sense? Yeah, because we have an x-intercept at 3, so that makes sense. And -1 was what? What'd you get, Aiden?
-4.
-4, anyone else sub that in yet? Yeah, okay, thank you. You're not lying to me, are you?
Nope.
You wouldn't do that? Okay, so here's our critical points. They are at -3, 0, and -1, -4. Okay, we don't know exactly what these are just yet, but I'm going to box it up. Okay, as far as like local max, local min, that kind of idea. Okay, and before we start doing charts or anything like that, we're going to find the second derivative, find point of inflection, and then we'll do it all together. So second derivative, here we go. I'm going to work off of this first line right here. So 6x plus 12. I'm interested in where that's equal to 0, as always, which should be negative 2. Okay, and then again, I just want to evaluate in the original function to get the xy coordinate of that point of inflection. Negative 2? Yeah? Did you get negative 2?
No, I think I did it wrong.
Okay, let's get some consensus here. I just did it in my head, so.
It's like a
Okay, I think I'm right. Negative 2 it is. I actually have the answer like right next to me, so I could check. Yeah, it's negative 2. Point of inflection. Negative 2, negative 2. Zainab?
For the x-intercepts, why did you put in 3, negative 3 for that?
For, like, above these x-intercepts?
Yeah, why did you take it to 3? Why did you not have that negative 3?
Because x-intercepts are where the y-coordinate is equal to 0, so I don't need to plug them in. I mean, you can plug them in if you want. You're just going to get 0 for both of them. Okay, so our point of inflection is negative 2, negative 2. That is where we change concavity. Okay, so we've got that. That's good. Okay, so when we set up our chart here, we're actually going to set up the chart with all critical x's and the x for the point of inflection, lowest to highest, okay? And we're going to set up in our chart the first derivative and also the second derivative, okay? So here's how I'm going to set up my chart. I want 3 sections here. It's a negative 1. Negatives. Okay, so all critical points, all points of inflection, just the x coordinates, of course. And I usually like to label these guys down at the bottom. So this guy was a critical number, this guy was a point of inflection, and this guy is a critical number. And the critical numbers, I'm just going to try, if I can, to identify those kind of as we're going here. So if I change from increasing to decreasing, for instance, then I'll identify that critical number as a local max. Okay, we need some test values in these areas. Hi. Miowa? No Lewis. Oh, yeah. I was about to say no Lewis here, but. Okay, so for this column, we're plugging these test values into the first derivative. For this column, we're plugging them into the second derivative, and I'm interested again in just like positive or negative, okay? So we're gonna take a second to do that. Imagine that you're plugging them in. So here, negative times negative, I think we get positive, negative. This one gives us negative. This one gives us positive. Okay, and then into the second derivative, this one should be pretty easy. This gives us negative, negative, positive, positive. No, that's, so in, in advanced functions, we multiplied them together because they were like rational expressions. But here's what I know. I know because the first derivative is positive in this section that the function is increasing, and because the second derivative is negative, I know that it's concave down. So what is this exactly going to look like? Well, increasing and concave down looks kind of like this, right? It's going up toward the right, but it's in kind of like a concave down shape right there. Okay, and then we've got a critical number, or critical point. And then my function starts decreasing, but it stays concave down. Okay, I know it's decreasing because the first derivative is negative. So still concave down, but now it kind of is going like this, right? Down toward the right. Okay, so I think we can identify our critical number here. Is this a local max or a local min? Yeah. Amazing, eh? Okay, now we have a point of inflection. This should tell me that we're probably changing concavity here. Okay, so we are still decreasing, but now we've got a positive second derivative, so it's concave up. So I'm probably doing something like this. Sorry, that was a bad actually. Something like, oh. One more time, third time's a charm. Like so.
Isn't that increasing though?
No, we're just talking about the slope of the tangent.
But
So
isn't that-
think about so when we talk about the original function, if my pen is going down toward, as I move left to right, that's decreasing.
But isn't the slope like really negative, and then as it continues, it's becoming closer to 0?
Right, so that's why the second derivative is positive, because the slope is getting less and less negative.
Oh, okay.
Yeah.
Okay.
So you're thinking the slopes of the tangents,
Yeah.
we're thinking about the original function f of x. Okay, we have a critical number down here. You don't actually really have to draw this like this. If you want to draw the curve up here, you can. And then we are increasing and concave up. So we've got something like this going on. So can we identify our critical number here? Local max, local min? Local min. Cool. So this is kind of what my function should look like. So we're going to graph all of our intercepts. We're going to graph all of our critical numbers, critical points, and our points of inflection. And then we're going to kind of use this graph. However, before we do that, we're going to just write the intervals of increase, decrease, and concavity here. So intervals here of increase. So we're increasing where the first derivative is positive. So I'm increasing in this section right here, and I'm increasing in this section right here. Okay, so from negative infinity to negative 3, in union with negative 1 to infinity. I am decreasing. Do I need to exclude a point of inflection from my decreasing interval?
Yes.
I don't. Only where the first derivative is 0. Okay, so critical numbers we exclude from the decreasing or increasing intervals. Points of inflection I don't have to. Negative 2 is just a point of inflection. It's not where the first derivative equals 0. Where the first derivative equals 0, like negative 3 and negative 1, those should be excluded from my set.
So you could just do negative 3, negative 1.
Yeah, so we're going to go negative 3 to negative 1. Mark?
But what if you have something that does this, like, it's originally going concave down and then it goes like that?
Yeah, so the first derivative will be 0 there. So we'll exclude that point.
Okay.
Yeah.
So that's the only time you do that.
Yep.
That's not a point of inflection.
So if it's like increasing, it's both actually. So the first derivative will be 0 and also the second. Yeah. Sarah. I almost called you Rebecca again. I had to think.
So we don't include the point of inflection. Like, sorry, I'm a little confused on that.
So when I'm talking about increasing and decreasing intervals, I'm really just interested in the critical points. I want to exclude critical points from my interval. Because this guy, the negative 2, because we're putting everything together now, we just need to be mindful about what's a critical point and what's a point of inflection. The point of inflection doesn't need to be excluded from intervals of increase and decrease.
But isn't a point of inflection a critical number?
No, we would call critical numbers or critical points the area where the first derivative is equal to 0.
Oh, so we just classify this as that?
Yeah,
Cool, thank you.
good question. Okay, concave up. We are concave up in these. Well, actually, again, we don't have to exclude the points where the first derivative equals 0 from concave up. It's concave up, everywhere along here, so -2 to infinity, and concave down on the opposite interval. So in this area right here.
So why aren't you excluding the point of inflection?
I am excluding the point of inflection, which is -2. There's my intervals. I can't erase on here again, so that squiggly line is just going to have to stay. Yes?
Why are we sure concave, like up or down? Like, maybe
So this distinction is important, right? So when I'm talking about my second derivative, I don't need to exclude critical numbers. When I'm talking about my first derivative, there's no need for me to exclude points of inflection. So critical numbers should be included, excluded from the intervals of increase, decrease. Points of inflection need to be excluded from concave up, concave down intervals, not critical numbers. Okay, so it's important to remember that the critical numbers kind of go with the first derivative, and the point of inflection kind of goes with the second derivative. There's no need for me to exclude critical numbers from a second derivative concave up, concave down interval. Olivia.
So we exclude them from the first derivative, the critical numbers?
Yes, and exclude the points of inflection from concave up, concave down. Yep. Okay, can we sketch?
Yeah.
Okay. 0 and -3. Those are our x-intercepts. -2, -2 is a point of inflection. And -1, -4. Did I draw that right? I think I did. Yeah, that makes sense. Okay, what do we know? Okay, we have to kind of fill in some of the gaps here. What do we know about end behavior if my original function has a highest degree that's odd and the leading coefficient is positive? Zainab?
From negative to, like negative infinity to 0 to be increasing, going up in the y direction, and
I feel like you're making this too complicated.
then opposite directions, I guess.
Okay, good. So opposite end behavior, and it should be going up toward the right, like so. Something like this, right? So odd and positive. Okay, so I'm probably doing something like this, right? So that is helpful to know. And as I come toward -3, I want to bounce off of that, so that should make sense as well, because this is order 2. So we're bouncing. I'm making sure that I'm staying concave down for this entire interval. And then here's a point of inflection, so we're actually changing concavity, so we should be changing to concave up. This was a critical number, which we identified as a local min. Still concave up, and just finishing over this way. Okay, so I'm just trying to keep, maybe that's not the greatest sketch, but again, I can't erase, so. I want to just try to keep that second part as concave up as possible. I don't want to like curve around after that. Okay, so that's what our function looks like. Okay, just another note as well. You can extend that if you want. One other little note is that all cubics have symmetry, so I should expect if I'm graphing some kind of cubic that I have point symmetry. So you can make that note if you want. Yes. Yep. These were critical points right here. This and this. And this was our point of inflection. Cool?
Symmetry.
Okay, so we are going to analyze this function, the full function. So I've outlined for you guys above what a kind of full analysis looks like here. I'm going to help you out with the first couple because we have to do some fancy polynomial division here. So I will help you, and then I will let you guys work on the remainder to finish up. Okay, so first things first, I might just identify some of the key features of the original function, such as degree, which is even.
Did you say it was even because?
Highest exponent on an x is an even exponent. It's 4. This is degree 4. Okay, so tell me what we know about end behavior here. Do we need a little break before we continue this, or should we just go? Just do it? Okay. Okay. So what does this tell me about end behavior then?
It's this way.
U-shaped facing up. Okay, good. So something like this. Might have some turns in there somewhere. Is there any symmetry that we know of?
No, none. It's 4, 3, 2, 1.
Yeah. So it's neither even nor odd. Basically, the domain of all polynomial functions is all real numbers. So I don't think we really need to state domain here for a polynomial function. If you want to, knock yourself out. Have fun. So I'm interested in where this function is equal to 0, or in other words, I'm interested in finding the x-intercepts of this function. Find the highest exponent on an x. And if it's even or odd, that tells us either U-shaped or S-shaped.
Oh, the degrees.
Degree, yeah.
Oh, okay. The function's neither.
Yes, the function is neither. Okay, so how do I factor something like this?
You have to do synthetic division.
Okay, so how do I find a factor then?
You have to do the factors of 18.
Sarah?
Find the factors of A and then the factors of B and then put like M3 over A.
Okay, so this one has a leading coefficient of 1 though, so I think we can just write out the possible factors as far as factors of 18, right? So it'll be these. Okay, you could, if you wanted to, if you really, really want to, you can test every single one of these in your polynomial and find the factors. Where you get 0 is where we have a factor. Or you can find 1. You can test until you get 0 for 1, and you can do synthetic division. So it's up to you. You can test every single one of these to find all your factors, or we can do some tests.
What is this to find over?
We're finding a factor so that we can divide and get this factored so that we can get x-intercepts.
Plus 2 is a factor.
Okay, so we'll pretend we did some tests there. So,
That's his calculator has cool things.
No, I just started.
yeah, he was like plugging them in as I was talking.
That's big
I
cheese.
went to
Yeah, he just did it like.
Sarah.
He has his 2
I was
pencils.
plugging in negative
Left hand, right hand.
Are you sure, Eden? Can we trust you?
Hey, if you put f at -2, 0, yeah.
Okay.
Yeah.
Is it? Eden, did you miss 1
No, I
as
started
a
at 9.
factor?
And then
Oh.
I started.
He missed 1. I was about to do 1.
Okay, so we will do a quick division here with -2. So this is a reminder of synthetic division. We drop and then multiply and then add and multiply again and then add and then again and add and one more time and add. Mark.
It's like the function, like, how do we know it's not symmetrical?
So I'm looking, just by looking at the exponents here, if I see a mixture of even and odd, I'll say neither. Yeah, no problem. Okay, so work your way from left to right. This is remainder, constant, x, x squared, x cubed. So here's what we have so far for f at x. We have the factor that we divided by. Don't forget that. We have x cubed minus 7x squared plus 15x minus 9. One more time. Possible factors. We'll call this guy P at x.
So now we're looking for 9, right?
Yep.
What is happening?
I don't have enough room.
Oh, plus minus 3.
X minus 3 is a factor.
Is that the smallest one?
Why P of X?
I feel like, doesn't 1 work here?
Can we try
Yeah, 1 definitely works.
Aiden, why do you went press the one?
I start large and then go small.
Aiden, stop word.
Can I just plug it into my calculator? Because it can factor.
Sure. Okay, divide. Focus, people, focus. Don't forget the factor you divided by. Going nice and fast to factor this guy. Okay, there we go. We're factored. That was fun, eh?
Sure was. I'm a good factor.
Are we even done? Or is this just
No, this is just finding x-intercepts.
oh no, wait, there's more.
I might give you something you have to factor once, probably not twice. Okay, what are my x-intercepts?
Minus x is equal to minus 2, x is 1, and I don't know. You're not really excited about it.
We want to be marked. Can you stop?
They robbed us.
And 3, 0, order 2. Cool. Y-intercept. Sub in 0. We're evaluating f at 0, which gives us the constant, negative 18. Where am I? Where are you?
Oh wow.
So this is just my factoring over here. You can just do this. There's my factoring to find those x-intercepts.
Should it be negative 2, 0?
Yes, thank you. Negative. Okay, derivatives. F prime at x. I see some division in our future. If you can do this, you can do any of them.
It's using too much brain power. I need to technology right
Okay, so I'm interested in where this is equal to 0. I don't have a lot of room left on here. I'll do it down here. What are my possible factors of this polynomial?
1 over 4.
But are we doing something
1.
again?
We have to factor this one,
1
though.
over 2.
So factors of 21.
There you go. Wait, oh, 21.
Yes.
I
Over factors of 4. So 1 over 2, 1 over 4, 3 over 2, 3 over 4. 7 over 2, 7 over 4,
Okay, circle the largest number. Okay.
21 over 4, and 21 over 2.
Wait, I have a question.
Yes.
Can you scroll down to the synthetic?
Yep.
Shouldn't it be x minus 3? Oh, just kidding.
Good.
I saw x squared minus 6 when you were up, and then I don't know what.
Okay. Try -1, Eden. I feel like -1 might work. Yeah, -1 works. Okay, we found a factor. So -1 works. Yep. F prime at -1 gives us 0. Therefore, x plus 1 is a factor. And we will synthetically divide. I'm going to do it over here to the right. -1. Focus, people. I know you're not keeping up because you're talking.
No, I can't write that quickly. I'm trying to write neatly and Ms. McGill.
Oh, that's a challenge for you, eh?
No, I'm trying very hard. It takes a long time.
I'm trying to read his writing.
So it's not going very well.
I just don't want to take like all the time up today, so I want to go fast for the stuff that you guys supposedly already know.
Can't write that. See, that's
I just
all.
don't have
If I, an old and feeble woman, can do it, then you can do it.
Old and feeble.
Don't even ask out. I'm worried. Shut up. The answers are not. No, we can't go back.
Are you just not trying right now? Okay. You don't have a pen in your hand, so I don't know. Okay, so that's our division.
It's 7 over 2. It's 7 over 2.
That's my factory calculator. We're not dividing, we're not synthetic dividing yet, are we?
No, just regular factor. So what do we get? 4x,
X minus 3.
4x, and x. Is it? Negative 3
4.75.
and -7? 12, and yeah, that makes sense.
I'm missing 2. Oh. Why did I switch it just there?
Oh, why am I saying x cannot equal?
No,
Ah,
you have to continue.
How do you write this quickly, this neatly? It doesn't make any sense.
Okay, we're almost to the calculus part, guys. Well, I guess we're kind of into it a little bit, but
Wait, we just got to calculus?
I'm just lost. I like was writing really quick and then I just got lost.
I'm just like,
I'm just
all I'm doing here, like this right side is advanced function stuff, right? Like we're factoring.
What we're supposed to be
This is factoring. We're graphing the function.
Which one?
There's only one function that we're working with.
This is all just trying to factor.
What is happening? You're still in that one?
We already found the x-intercepts. This is all finding x-intercepts over on the right-hand side.
This side, right?
This is, yeah.
So the bottom's here.
Okay, shh, silence, children.
So it's negative.
I thought this was it. I don't know why.
Okay.
I don't know what the X is.
Shh, silence, silence. Okay, you have the critical numbers. We're gonna, plug them into the original function to get the y coordinates. Aiden's gonna do it for us.
Yeah.
Nice and quick.
-1 and -32.
So now we're doing this derivative test.
Wait, no.
We're gonna do second derivative in a second.
We're factoring f and x to get the things that we're finding the y values?
Yes.
We're doing right now?
Yeah.
But
Okay.
in English, don't say things like 10 times.
3. I'm recording it.
3-0.
No, not really.
Back. I could like hear
Technically, you're made of
Yeah, no, not really. But probably because you guys are so loud right now, it can probably hear you.
Hi.
Okay, Aiden, F at 3.
Is 0.
Okay.
And F at 7/4 is 11/25/256.
Carbohydrates, partially, yes. Saccharide.
Thank you.
Paul.
Here's our critical numbers, critical points. Now, we're going to find the second derivative.
Don't we need the first derivative?
We just did it.
Yeah, we just did it.
Oh, yes. I remember.
We're almost there, guys. We're so close. F prime prime at x. This one should be easy to factor because it's a quadratic. Lauren. So we just have to factor this. My guess is that it's probably this. So maybe not. No, it's probably... Is this factorable?
With quadratic formula only.
Oh boy.
Those are critical points, right? This isn't a lot of
This question.
Okay, so we are going to find the x's with quadratic formula.
X1 is 2.43.
2 point what?
2.43.
Yeah, you're right.
X2 is 0.0685.
I got 0. Oh, we'll just do 0.7.
You did it too calculated.
My factor calculator.
Oh my god.
Why does it say Q?
Quadratic formula. And we're going to find these. Shh. Like I said, if you can do this one, you can do anything. Anything. Even chemistry.
I don't know if this
Wait.
I don't know. I don't know if
That's a stretch, Mr. Guys.
Do we still have a quiz on this one?
1.058.
Just give us like one of these questions.
Yeah. No. Yes.
058?
Yep.
Why are you saying no?
No, it's not for marks. Okay, I'm going to give you, I'll just do this one. It's negative 16.5.
Olivia, you have to do quadratic formula in chemistry.
Yes.
There you go.
Because you do.
No, like, what would you like?
Vincent, you have to do quadratic formula. We can't tell you. If we tell you the future,
Sounds like a scam.
No, why do you need it more? Wait, let me guess.
Okay, if you didn't pay attention to anything else, you need to pay attention now. Okay? I said if you didn't pay attention to anything else, now would be the time to focus in, and we're going to do the chart, okay? That's what I'm more concerned with. Of course, I am concerned that you can find x's. That's important. But we should already have these skills. Yes?
The 2.43 and the 2.06, what are those? Those are points of interjection.
Points of inflection. So these are critical points, and these guys are points of inflection. Okay? So, again, if you haven't paid attention to anything, you can at least do the chart with us, okay?
I feel like in 200 years, if we go extinct and we find this, they're going to be like, what kind of language are they speaking?
Cool, good chat. Okay, I'm going to do my chart down here.
Okay, chart time.
Don't sigh, Aiden.
Sorry. It's on the right.
No, interpret it as a language.
1, 2, 3, 4, 5.
We should do a time capsule.
Wait, did you already do that?
1, 2, 3, 4, 5. I'm making the chart.
I'm really confused. Where did you go from? What was your Y value for
That's part of my contract.
Shh. Okay, we're going to play a fun game.
1, 2, 10.
Anyone who talks loses. It's called the silent game. It's really fun.
Ryan.
That's it. Ryan gets detention.
Okay. Well, guys.
Okay. Good? Someone was asking me about those numbers? These guys? Because we want the point. The xy coordinate. Okay, I'm going to line up all of my critical numbers and points of inflection, like so. And I'm going to choose test values. This is like the ultimate question, guys. This is like all of your skills have been leading you up to this moment.
Full day.
Hey, lost, he talked.
You know, if I
Aiden, you get a detention.
so smart. I'm not even
Why are you so big? Why would
Yes, thank you. Thank you. Thank you, Jesus. Olivia.
Why did you do a -2? Why did you go all the way to -10?
I don't know, just for fun. You know, sometimes I like to live on the edge. Okay, I'm going to fill this in for you guys because I'm nice. And I trust that you can plug these into your first and second derivatives. I know, I believe in you.
Oh my gosh. Wait, any other shot? Wait, Miss Michaelis, can I show you a math question after? I want to see if you want to. No,
Sure.
It's actually like a massive brain.
Okay, focus into this last part. So I am decreasing and concave up, which means I'm doing something like this right here. Also, what? Yeah. I actually do want to do that. This is a critical number, and this is a point of inflection, and critical number, and then point of inflection, and critical number. Okay. And then I am increasing and concave up, so something like this. And can we identify that critical number? Local? Min. Okay, now we are increasing and concave down. So this is a point of inflection, so I should have expected to change there, so like so. Critical number, and now we are decreasing and concave down. Very good, local max. Beautiful. Point of inflection, and we are decreasing and concave up now. So something like so. Critical number, and last one, increasing and concave up. This one's a min, good. So now all that's left to do is create our super accurate, amazing sketch. Sarah's just like staring at me like so mad right now.
How accurate is this sketch?
It's gonna be so accurate. It's gonna blow your mind. Okay, plot. Yeah.
Why are you taking my joke?
Oh, okay. Plot your x-intercepts. There's our x-intercepts. Our y-intercept was at -18, so we might want to go by like, I don't know, what do we want to go here? 2, 4, 6, 8, 10, 12, 14, 16, 18. Sure. We'll go by 2s. I know. It's amazing, eh? Okay, plot your critical points. Negative, oh no. I didn't make my scale big enough. Oh.
Why?
the line valve. Stop what you're doing. Do not.
Because one of our critical numbers is at -32, isn't it? Yeah, it is.
That's a
Just like stick that one out.
Yeah, we can
That is unforgivable.
Out of all of this, that's the part that's unforgivable. I can't even erase on my thing here, so.
Plus 2% on my next test. That's how it should be.
What? I'm just gonna reopen it so that we can. What just happened? Oh no, sorry.
52 is the next line. If it didn't get saved, do it all over again.
No, don't worry. It's here. Oh, my eraser still. Oh, yeah, it works. Yay.
I'm gonna make it up.
Aiden, can you calculate the number 1125 over 256 for me?
4.39.
Okay, so we're good then. If we can get up to
Yeah.
-32. 5, 10, 15, 20, 25, 30, 35. Let's do that. We'll go by fives. Mark Mancarius. Silence. Hopefully he's just like, okay. Okay, we're almost done, guys. I should have what? Like Mr. Jensen? Did you just say?
What'd you say, Ryan?
That's Aiden's favorite teacher, so.
Has his own like website and stuff.
I have my own website. It's called Edsby.
Yeah.
Dude,
She has a bunch of YouTube videos.
Yeah, can you make a YouTube channel? I'll subscribe.
No, I brought you.
I subscribed. I
I'm
subscribed.
sorry. I subscribed your class. No one told me.
You know how in every journal every day I post a lesson video link?
Yeah.
I thought it was just like for fun, like content.
No, it's one more.
Yes, locked me out of
Okay, I'm just gonna finish this, and if you want to copy it, you can, and if you don't, then you might fail. I don't know. I know. I went there. This might be the only test question. I don't know.
Oh, actually, that would be a good idea.
I don't know. You can't.
That would be like Mr. Sankfish.
Yeah.
Oh,
I don't know
do
if we
that.
did that like part F and G on like on one.
Guys, stop.
Who's this?
Yeah, this one. How about we just do regular school like it's been for like decades?
How about
Like this new convention.
Mark, don't you want to adapt?
No, I don't.
Vertical surfaces.
One question has
Wait, are we going by one? We're going by one.
Yeah, that's what it is. What is that? I'm confused about which points apply. Yeah, what do you
I never
mean?
Everything. All the points.
Oh, she plotted the decimal.
You're confused because no one's listening. That's why you're confused. Olivia, yes.
The x-axis, they're always going by one, right?
Oh, sorry. Yeah, the X's are going by 1. Sorry, this guy's down here at 16. Right here. Okay, here we go. Positive, leading coefficient, concave up until this, and then it's concave down, hitting a max, and then it's concave up, and we're done.
And you're going from negative
So that's what that looks like.
That's all you.
Thank you. Thank you. Yeah. So this whole section up to the red point right here is concave up.
It's not a tie. It's
Right there.
$5 on diet. Wait, leave our stuff in here.
Yeah, you guys can leave your stuff.